Hi, and welcome to our new session here in our chapter on risk minimization, or I guess advanced risk minimization. And this session here might be just a tad bit more advanced, so I want to at least briefly introduce what proper scoring rules are. I guess this is an important but sometimes not so much discussed concept in, introductory MML courses at least. And at least when I was a little bit younger and read papers about this and tried to understand this, it took me a little bit of time to properly understand that and properly connect that to things like empirical risk minimization. So I guess I'm trying to make this a little bit easier here for you. So here in this chapter, in this session, we will learn what proper scoring rules are, what strictly proper scoring rules are. We'll discuss a so-called first order condition on the loss function, so that this might actually be turned into a proper scoring rule or might be, identified as a proper scoring rule. And we'll discuss a couple of examples. So log loss and Breyer score are actually strictly proper scoring rules. We'll discuss one example which is not. So that's L1 loss on probabilities. And we'll discuss the 0-1 loss in classification as an example which is proper but not strictly proper. I guess let's just start, right? Let's just figure out what proper scoring rules actually are. So the whole motivation for this is to discuss whether specific loss functions are for probabilistic classifiers. So I will use binary classification and probabilistic classifiers for binary classification as a, I don't want to say running example, let's say context here, scenario to discuss proper scoring rules. You can do this in general also for regression and other outcomes and so on. I just want to stick to a simple and common scenario, so to speak. And what we want to do is we want to discuss whether this guy here, this loss function, is actually reasonable. Yeah? And I guess for this we need some form of a mathematical definition of what we mean with that. What do we mean with reasonable? Okay, so let's do that and have a little bit of patience. So I just want to now formally specify what I mean with a scoring rule and a proper scoring rule. So a scoring rule is pretty much just a loss function first and for all. So you can call things that measure a distance between some observed label y and some probability distribution. You can already call that a scoring rule. And this is exactly what I'm going to do. So usually there's in the papers, there's this really nice paper here by Knighting and Raftery, and I really recommend reading that, but this might be, on first try a little bit harder for you if you haven't read too many more advanced theoretical texts in statistical learning. So this uses a slightly different notation, and sometimes scoring rules are also usually maximized instead of minimized. So like I've said, I'm trying to connect this here as ideally as I can to the concepts we already know from empirical risk minimization. So what we now want to do is we want to just give that thing a slightly different notation. So sometimes we'll use this S here S for scoring rule. And I am also going to generalize this just very, very slightly. So I'm going to say that a scoring rule actually compares two distributions. So there is the predictive distribution, and I will simply now use a capital P for that. So I could have also written pi or pi of x. Later we will also maybe do that. But here for this definition, I will just use capital P because we have been using that for general distributions before here in this lecture. And then there is the distribution of our labels. So I'll just label, no pun intended, I'll label that with a Q, denote that with a capital Q. So Q is how our labels Y are distributed, and P, capital P, is a predictive distribution. And what we will now do is we will say this scoring rule here compares these two distributions by being based on a loss function, and we simply take the expectation over our labels Y when they are distributed by Q. That's it. So this is pretty much just expected loss. We are writing this slightly differently now, and we have of course looked at this before, especially in the beginning of this chapter. Actually pretty much, in many sections, I guess we have minimized these things. We've talked about risk minimizers and so on. So we've looked at this quite often. And we've also seen that we can look at this conditionally, which is what we're mostly interested in. So conditionally at some feature vector x, and then we're going to construct the optimal predictive distribution under a certain feature vector x, so at a certain point in feature space. But we could also look at this theoretically unconditionally, and then the kind of the concepts and the derivations and so on, the results, they're basically pretty much the same, and just writing down the x and conditioning on it always is annoying and tedious a little bit. And we can also look at it empirically, we can look at it theoretically, and then again, there are very, very strong, connections, and having the one result, in the theoretical domain gives us already the empirical result and so on. So this should be pretty familiar to us, I want to say. And like I said, minimizing this expected loss then gives us the risk minimizer, especially if I would do that conditionally. But like I said, I can also do this unconditionally. And then I've sometimes called that the optimal constant and so on. But here we're talking about probabilistic classifiers. So I'm minimizing over this guy here, and that's a distribution, right? Even if I can represent it as a constant vector, with 3 elements. So maybe this is, we have 3 classes, and then the result might be something like 0.1, 0.7, and 0.2. So 3 probabilities for 3 classes. That's obviously probability distribution, right? So that's a probabilistic classifier. Okay, so give me a few, not too many minutes to motivate what I mean with this reasonable loss function. And we need one extra concept now, which is also not too difficult to explain. So we will now call such a scoring rule proper if the true label distribution Q is among its optimal solutions when we maximize this scoring rule with respect to the second argument. So that sounds difficult, but it really is not. So the thing is, we pick some arbitrary distribution Q because that's our label distribution, right? That comes from our, data generating process. It's some arbitrary label distribution that we have no control over. But we do have control over this predictive distribution, and our loss function should guide us towards finding an optimal one, right? It's going to do that, right? I guess pretty automatically, because we are going to minimize, right? And we're going to minimize in expectation, at least in theory, right? And ERM is then, the empirical approximation of that. So we wanna optimize this guy here in the, excuse my very terrible scribbling. I wanna optimize this here in the second argument for a prescribed Q. And what I mean by this statement before, that the true label distribution Q is among the optimal solutions for any arbitrary given Q, I can equivalently simply state that if I insert my true label distribution as the predictive distribution, so I have some form of an oracle, I know this, I know what the true label distribution is, and I just use that as a predictive distribution. This is always at least as good as any other distribution Q I'm picking. And if this is true for all P and all Q, then I know that for a given Q, Q itself must be an optimal predictive distribution. It doesn't necessarily have to be unique. There can be other solutions, but the true distribution, the true label distribution, optimizes my scoring rule. And if you look at this conditionally and just use, different symbols that we've introduced before, and that's sometimes a little bit confusing, that we have all of these, different symbols going on here, but hopefully this is not too hard to understand. So I could also look at this conditionally, right? And conditionally, I would now talk here about this risk minimizer, what we have always denoted with pi star of, x tilde, pi star function of x. And this here is the true conditional distribution, right? So this means that my risk minimizer, that one admissible solution for my risk minimizer is this thing here, And before I was I wasn't super rigorous with specifying this pi star. We defined that as an argmin, to this loss minimization problem, to the theoretical risk minimization problem. And yeah, argmins, they don't necessarily have to be unique, right? So I don't know if I would have wanted to be super precise, maybe I should have done that. That's going to be a set, right? It can contain multiple solutions. So if our proper scoring rule is just proper and not strictly proper, that means that this true distribution here is among the potential risk minimizers, is among the risk minimizers. And we'll now just say, I guess that's not going to come as a super big surprise, that our scoring rule is actually strictly proper when our definition above here holds with equality. Yeah. So, sorry, holds with equality. Yeah. If and only if P equals Q. And that means, if we require that, that means that there can only be one unique solution, and this one unique solution is going to be our true label distribution Q. And this means that our risk minimizer is actually unique, and it's going to be this conditional distribution pi, probability of y equals 1 given x. And using such a proper scoring rule actually ensures that the optimization of such a proper scoring rule, and henceforth the optimization, the risk minimization of the associated loss function and of the associated ERM problem, so to speak, pushes our solution into, towards the correct distribution, which is the true label distribution. And that seems something really reasonable. Unfortunately, as it turns out, that is not necessarily true for all of the loss functions we have looked at currently. So let's look at an example now where we can actually show that a loss function is not a proper scoring rule, and that what we just deemed as reasonable is not necessarily true. And the L1 loss on probabilities is actually such an example where we have a non-proper scoring rule in front of us. So I'm not going to, write this down conditionally now. I don't want to always write conditioning on x is pi of x, because this is not going to add in any extra value, so I'll just leave that out. I look at things unconditionally because that really doesn't change anything. And I will assume that my targets are binary. Well, I've said that before, it's binary classification, 0, 1 labels. So they come from a Bernoulli distribution. And this Bernoulli distribution has a parameter eta, and that's my true probability of things being from class 1. That's class 0, and that has true probability 1 minus eta. What we've looked at before is that if we now compute the expected loss, we can very slightly expand that in the following form here. It's going to be eta times the loss between label 1 and predictive distribution pi, or probability pi. This is our predictor, written down here as an unconditional form, so constant, I don't know. Like I said, that doesn't change anything. And 1 minus eta times loss between label 0 and pi again. Okay, so let's simply now insert L1 loss into this little formula here. So L1 loss, L1 loss on probabilities. So we take a 0, 1 label, we look at our predicted probability, and we just compute the absolute difference between the two, as we would do this for L1 loss in regression. And that's the loss function that exists. It's used a little bit less in machine learning, maybe because of this fact here that I'm going to show, but it exists. And I've introduced it before, and why not consider it? Maybe it doesn't seem, at first glance, it doesn't seem to be totally unreasonable, right? Actually, L1 loss for regression sounds super reasonable. So actually squaring this might sound weird. So why not use this thing here? So let's insert this into the formula above, and we can very easily show that this is here the result. Just inserting that, handling the two cases with the 0 and the 1. I'm not going to do that here with my pen tool. I'm not going to even read this out because this is like super simple. You can do this yourself in pretty much a second. Just inserting the thing, removing the absolute value for the 0 and for the 1 case, and then just, reordering terms a little bit. Now let's look at this. Let's rather look at this and think about how we can actually minimize that. So first of all, eta is a constant, right? It's, I don't know, potentially unknown to us, but it's a constant. And pi is the thing we want to optimize over. And we want to minimize this thing, right? So what type of a function is this here? So it only contains eta and pi, and it's a linear function, right, in pi. So linear functions are really easy to optimize. Actually, they wouldn't really have a minimum. But this thing here is box constrained, right? So we know that pi cannot be less than 0, and it cannot be larger than 1, because it is a predictive probability. So let's just consider two cases. So let's just think about what sign this thing here has, which is 1 minus 2 times eta. So if eta is more than 50%, well, then this thing is going to be negative, right? And if this is negative, we have our interval here, I don't know, going on from 0 to 1. And there is some function now, which I don't know, somehow looks like this, right? So it has some negative slope. And pretty clear that the minimum is going to be here at the right boundary of my 0, 1 interval, which means in this case, pi star, which is the risk minimizer, which is the solution to this simple optimization problem, is going to be 1. If eta is less than 50%, and then this thing here has a positive sign, if a case like that, with a positive slope, and then our minimum is here on the left-hand side, and that's 0. Now, what we do have to do now is we have to compare this with our prescribed eta value. Our eta value was arbitrary, right? It's some Bernoulli distribution with some eta. I have no idea what that is. And what we wanted from a proper scoring rule was that the minimizer was always eta, or eta was at least among the minimizers. But what we have actually now shown is that the true eta is actually worse than this pi star. Well, maybe I shouldn't have removed this here, but like, I don't know. Let's maybe do, I don't know, this example here again. So with a positive slope, so in that, I guess that would be this case here. So eta is somewhere below 50%. So maybe it's here. This would be our expected loss. But this expected loss is actually smaller. It's very clear, yeah, for this linear function with a non-zero slope. So like in nearly all of the cases, I guess, except for extreme cases where eta would be exactly 0 or 1, this true eta is worse than our risk minimizer. So our L1 loss on probabilities is not even a proper scoring rule. And this might actually mean that optimizing that pushes us to very extreme solutions, right? So our probabilities at the end that we'll produce, if we would optimize machine learning models with such a loss, might be what we would call very badly calibrated. So although they potentially might be something like, I don't know, 30% or so, we would push them towards the extreme end, which is, I guess, for these smaller probabilities, 0, and for larger probabilities, 1. And that's going to be the effect of that. And we just figured out that this is a potential problem for this loss function. And I guess that's a reason why theory is sometimes useful for understanding things. Or I don't know. Often. Oh, well, let's stay with sometimes. Here's another loss function and another very similar analysis. So we now use 0, 1 loss. So 0, 1 loss, we have seen this before, more or less defined on hard labels. Yeah, so we have some hard labeler H, which is outputting 0, 1 labels, and then just compare them to the true underlying label, to the true Y label. Yeah, and if it's different, it's going to be a 1, a loss of a 1, and if it's the same, it's going to be 0. But here, I want to do this for probabilistic classifiers, so I'll just turn my probabilistic classifier into a hard labeler by thresholding at 50%. So if my pi value is larger than 50%, I'm going to say 1, I'm predicting 1, and if it's less than 50%, I'm just predicting a 0 in the natural manner. Now, what's the expected loss of this? We again use this nice little formula here. We again plug in our loss. It's very easy to see now. So if our hard label actually produces a 0 value, this means that, well, let's remove a little bit scribbling. So if we produce a 0, then I guess for this case here, the measured loss between 0 and 0 is going to be 0, right? Because it's going to be correct prediction. So we only have this thing here. And now this loss here is going to be a 1. So result is just error. And if you do this for h equals 1, so for this case, this will vanish. This is going to be 1. And we have this thing here. So our loss function, our expected loss, which is a result of our scoring rule. There's actually an L missing here. Sorry. It should be expectation of L. Sorry for this typo. This takes exactly 2 values. So if a function takes exactly 2 values here, maybe it's not too hard to minimize such a function. So let's just think about our eta again and do a case-by-case analysis. So if eta is larger than 50%, then, well, I guess this here is larger and this here is smaller. So if we want to minimize, I guess we better take that thing here. That thing we take if our h function produces a 1. And when does our h function produce a 1? Well, if this is true here, right? So if our pi prediction, and that's our probabilistic classifier, has a value, has a distribution which is larger than 50%. So the thing is now any value in this interval here from 50% to 1 actually minimizes my expected loss. And we can do exactly the same type of analysis for eta being smaller than 50%. Well, if it's smaller than 50%, we want to be here. So we want h to be 0. So we need pi to be in this interval. Let's look at these 2 intervals and compare them with eta, and we can clearly see in both cases eta is in this interval. So our true probability, our true label distribution is among the minimizers. And that's exactly what we want. So, and this is actually a proper scoring rule. That was exactly what we wanted and what we required of a scoring rule being proper. On the other hand, you can also clearly see that this rule here doesn't really discriminate very strongly between many different solutions, because there's like this whole super large interval of different solutions, and they are all the same to us under this loss function, right? So this eta is not our unique minimizer. So we're not super happy about this. We are partially happy because it is a proper scoring rule, but it's not strictly proper. And it actually, I guess I've explained it well enough. It kind of weighs too many different predictive distributions equally. Yeah, as long as they are on the correct side of the threshold, on the correct side of 50%, I can't discriminate between them. So what we could now do is we could just try out different other scoring rules and show that they are proper and strictly proper, but I want to do one little thing before, and this is, I want to actually ask myself, maybe I can just find a certain property of a loss function so that it actually is proper or strictly proper, and that's actually possible. There's a certain so-called first order condition, and actually it's very easy to derive this, so how about we just do this here. So how do we now have to define our L so that our risk minimizer is actually eta? So in order to simplify things here a little bit, I'm going to assume something about my loss function, which is not super restrictive. So I'm going to assume a certain form of symmetry, because I really hate writing this here with a 1 and with a 0, and then I have like these two potentially different functions, depending on what label y I insert there. So what I want is that so I'll just say that the loss here, if I compare 1 and pi, I'll just call that my loss function, and I'll write that in argument pi. And I will assume that the loss between label 0 and pi is the same function if I evaluate that at the counter probability, so 1 minus pi. If you, I don't know, if you see this for the first time, you might say, oh, that looks a little bit strange. What does that actually mean? Actually, it's very simple. It means that Well, just think about how I have visualized these loss functions before, and then kind of have struggled a little bit with the fact that, yeah, that they can potentially be two different functions, right? And there's no way of representing that nicely with a single function. So just plotted two, right? I plotted this for y equals 1 and y equals 0. But in pretty much all of the cases we looked at, there was a very strong symmetry going on at the point pi equals 50%. Yeah? So both of these functions are just mirror images of each other. And with respect to this, to this line here at pi equals 50%, so they're effectively the same function. Yeah, and I wouldn't necessarily have to talk about both of these. They could be in general, they could be different, but very often they're not. And if this symmetry exists, or I'm just going to assume that this symmetry exists, and then I can actually write it just in terms of pi, which effectively means that I'm just looking at this yellow guy here. Yeah, because this is this L1 pi thing. So also not super difficult, and that allows me to, I don't know, now directly work with just one function, and I'm going to take derivatives now and minimize directly. Yeah, okay, let's maybe do this slowly. So again, I'm going to use my eta here, which is the probability of y being 1. I'm going to look at this expected loss here, and I'm going to use the same formula as before, so absolutely no difference. Now, because I want to minimize this, I'm going to assume that L is differentiable. I guess I should have put that on the slide as well. It also doesn't necessarily have to be true, but I'm going to assume that this is differentiable, maybe even twice, maybe in a continuous manner. So let's just, like, I don't know, fiddle around with this a little bit and see where we can go. So well, what do we now want to do? We want to minimize this thing, right? So I guess we take the derivative. This is a univariate function, just in pi, in a single value. So we take the derivative, and our minimum needs to be a stationary point. So I guess we require that. And then we also require that at the minimum, the minimum is actually at eta, yeah, and not somewhere else. So if I do that, and maybe you have to use your pen and paper here for, I don't know, a second. I guess maybe you can even do this mentally. It's really not hard. So, well, I guess we could also do this together. So if I take the derivative of this thing here, so let me remove all of my terrible scribblings. So this constant here stays. This is going to be L prime. Yeah, so we have this here, we have this. This is a constant, this stays. This here, for this I have to do a slight application of the chain rule. So this is going to be L prime of 1 minus eta, and then there's a minus 1 from the inner part, which means that this thing here will be a minus. So I can just now put terms on different sides of the equality sign, and now we have arrived at our so-called first order condition. So this first order condition must be fulfilled for a function to be a proper scoring rule. And then if you potentially can even show that the second derivative of this function is going to be strictly positive, then you would have strict convexity, and you also would know that this minimizer, the stationary point, is a unique minimum. So let's just do exactly that. Let's figure out whether there are solutions to this equation here. So what type of equation is that actually? It's actually something like you might be less used to, because we're now reasoning about functions. Yeah? We are reasoning about functions L, capital L, and there are derivatives going on here. So this is what we would call a functional differential equation. And they might be a little bit harder to solve, and don't want to go into this here now. To be completely honest, I'm also not super sure whether we can proceed way smarter than we are here on this slide. But anyhow, what I now just want to do is I just want to guess solutions. Okay, I want to look at that thing, want to become a little bit creative and think about what type of an L prime function would actually be admissible here. Oh, and I guess I forgot something. We don't only have to compute the derivative, we also have to do one very simple thing. We now have to insert for all of the pi values our eta, because that's what we want, right? That our risk minimizer is actually at eta. So we have to do that, and then that gives us the first order condition. And now let's look at this. So what solution could we use? So I guess, hopefully you can very easily see and check that if you set L prime to -1 divided by eta, well, that is obviously a solution, right? Because this here becomes -1 and this here becomes -1 as well. So both sides are the same. This is exactly what we want. Now, we are not so much interested in L prime, we are more interested in L. So how about we integrate that? So let's form the antiderivative. And for minus eta, this is going to be minus log, right? Minus log of eta. So that's our antiderivative L, but we are not used in writing that function as a single argument for losses, right? We have losses with this ly comma pi thing going on, right? So what we have used this slightly weird abbreviation here, right? So how about we just do that now in reverse? And you can easily check that if you do that, then for this thing here, for this one argument loss function, that corresponds to this thing here. Yeah, just again, check it out. Just do that thing here in reverse, and you will immediately see that this corresponds to this 2-argument loss function. Really, you can just also easily see this, right? So we have this term here, which is for the y equals 1 part, and this is here for the y equals 0 part. But we do know this guy, right? That's log loss, that's Bernoulli loss. So we can immediately now see that our log loss satisfies this condition, it satisfies this first order condition. It is going to be a proper scoring rule, and it's also a strictly proper scoring rule, because you can easily check that log loss, if you take the second derivative of this, and I guess you want to then take the second derivative of this thing here. What is that actually? L double prime of pi is just 1 divided by pi squared. As long as we're not extreme, so if pi is not 0 or 1, this is always going to be strictly positive. So we have a strictly convex function in front of us. So the minimizer is going to be unique. So we have a strictly proper scoring rule. There's also a second potential solution, which is not that much harder to detect. You can also, maybe you need a few more minutes to figure that out. But this thing here is also a potential solution to our first order condition. Again, you can very easily form the antiderivative, which is this thing here. And I guess you can now already see where this is going. If again, do this thing here in reverse, you can form the 2-argument loss function, and that's y minus pi squared. And that's Breyer score. And I guess for Breyer score, there's already the score also in the name. And I guess that might come also from the fact that this is actually proper scoring rule. Actually, historically, I'm not super sure about this, but I will guess. And again, you can do the second derivative. It's just a quadratic function, right? It's easy to do. It's also going to be strictly positive. So this is again a strictly proper scoring rule. Nice. That already brings us to the end of this session here. So yeah, like I said, usually these scoring rules, they are sometimes maximized. I adapted notation here a little bit for us. I wanted to simplify things, yeah. Compare this maybe by the Guiding paper. Yeah, maybe you find this a little bit harder to read. Maybe you find this simple. I don't know. I found this a little bit harder when I tried this the first time. I need to do this mental translation a little bit. If you want to know more about proper scoring rules, there's a lot more theory going on. There's a lot more you can do with this and learn about this. I would say this paper is an excellent starting point. You will also then figure out that this does not only work for binary classification. I've done this here because it's a little bit easier to explain that. And it's also quite common to do that, but proper scoring rules can be defined in general for arbitrary targets. And there are also other proper scoring rules, like the so-called generalized entropy score or the so-called continuous rank probability score. I want to keep things simple here, although these things are interesting and important. I don't want to go into them now. That brings us to the end of this session. I hope you didn't find this too difficult, enjoyed this, learned something. See you in the next session. Bye-bye.